Welcome everybody to the not yet last of this Splinter. So we're gonna hear now from David Coria and talking about plant deformation and emerging history from isotopology. So take it away.
Yeah, hi, can everyone hear me okay? I can hear myself, okay. So first of all, thank you to Jackie and Aaron for organizing this awesome Splinter session. So my name is David Coria and I'm a fifth-year grad student, so I will be on the job market soon. Just keep that in mind as you listen to me. But I work at the University of Kansas with Ian Crossfield and Neda Hijazi to derive stellar abundances for mostly cool dwarf stars. But this particular talk was inspired by some recent and pretty remarkable detections of carbon, nitrogen, oxygen isotope logs in these cool worlds. So thank you to Ben and Melanie for sort of like introducing that. But my goal here is to kind of share how these particular abundance ratios can help us distinguish between different formation, migration, and accretion scenarios for these different objects. So the main question that we're trying to answer is, how do we study the chemistry of the formation of these cool worlds? One of the ways that we do this is by characterizing the building blocks themselves. So in certain protoplanetary disks like those pictured here, it's actually possible to make inferences on the composition of the gas and solids that will eventually become planets. Another approach to understanding planet formation and the evolution is to consider what happens to planets from birth to adulthood. So using these planetary growth models, we can sort of infer how planet atmospheres change as they migrate and accrete different materials throughout the disk. But more importantly, we can use these predictions to sort of tie in planetary abundance measurements to the chemical composition observed in protoplanetary disks and to the planet's host stars. And then the sort of final approach that I want to kind of use to motivate this is to consider what a planet does and doesn't inherit from its host star. Typically, exoplanet abundance measurements are compared to solar values, but especially in these systems with stellar companions, best practice says that we should actually characterize the host star to properly contextualize the exoplanet constraints. Cool dwarf star abundances are highly sought after as a complement because they serve as a sort of proxy to the chemical inventory of the protoplanetary disk. However, especially for K and M dwarf stars, they're notoriously difficult to model because of all this overwhelming molecular absorption and blending that dominates the optical spectra that we typically have on hand. But nevertheless, we've had some success in fitting cool dwarf star spectra and in measuring elemental abundances in the near infrared. And this means that we're now able to sort of infer formation migration scenarios for individual exoplanets and their host stars. And so this is kind of like the area where I spend most of my time researching. One of the goals for the KU EXO lab is to derive stellar abundances to better contextualize exoplanet atmospheres. So I'll take just a minute to promote our lab's new code called AutoSpecFit for fitting stellar spectra iteratively and then deriving their abundances. And it's led by Neda Hijazi sitting here in the audience. So I'll leave out the specifics, but if you're interested, please refer to Hijazi et al. In 2023 to see how this code is applied to WASP 107. Keep an eye out for our K218 abundance analysis currently in review, and also look out for the public release of this AutoSpecFit code coming soon. But for the rest of my talk, we'll be discussing carbon, nitrogen, oxygen abundances, and how we can sort of use them to infer a planet's formation, migration, and accretion history. So it's generally accepted that brown dwarfs form like stars from the top down via gravitational instability, while the superjupiters form more like planets from the bottom up via core accretion. But what people may not know is that each of these processes leaves behind unique carbon-oxygen signatures in the atmospheres of these substellar objects. So, for example, brown dwarfs form rapidly on sub-megayear timescales, and thus they're expected to inherit stellar to superstellar carbon to oxygen ratios and abundances. So kind of like what happens in binary star formation. Core accretion, on the other hand, is a much slower process, which means that these Jupiters can incorporate varying quantities of gas and solids into their atmospheres, potentially resulting in a pretty wide range of atmospheric metallicities and C to O ratios, but still maintaining those substellar carbon-oxygen abundances. In general, these are the main chemical differences that distinguish the brown dwarfs from superjupiters, but as you heard from Melanie, D to H is starting to become something that we may want to look at as well. But in addition to distinguishing between different formation processes, volatile abundances can also be used to infer different planetary migration scenarios. So the C to O ratio is a particularly good tracer of a planet's accretion history because the gas phase C to O ratio increases with distance from the host star. Besides carbon to oxygen, though, there are other volatile ratios like carbon to nitrogen, nitrogen to oxygen, and sulfur to nitrogen that also seem to deviate from stellar values, especially in these models, depending on the extent of the migration that has occurred. So ideally, depending on where in the stellar disk a planet forms or accretes its envelope, we expect to measure different ratios of volatile elements in the planet's atmosphere. Then by measuring the host star's abundances, we can sort of gauge the extent of the migration. But of course, mapping a planet's measured composition to a specific formation pathway is not really like a one-to-one process. But with the host star and companion abundance constraints, along with these really sophisticated planetary growth models, we can better disentangle between the degeneracies. Sorry. So nowadays, especially with data from JWST and these ground-based high-resolution spectrographs, we suddenly gain the sensitivity to weaker isotopolog signatures that we wouldn't see otherwise. And these isotopic abundance ratios provide us an additional constraints for planet formation migration scenarios that we can potentially measure in both the host stars and their companion planets. So starting off with the carbon-12 to carbon-13 ratio, in general, what we expect for planets that form within the CO snowline, which is around 20 AU and solar type stars, we expect them to inherit their host star's carbon-12 to carbon-13 ratio. Beyond these snowlines, however, there are certain fractionation mechanisms that result in partitioning between the major and minor isotopologs, which can create different reservoirs of carbon-13 rich gas or ice. So this means that a planet that forms in the outer portions of the disk may exhibit a much lower carbon-12 to carbon-13 ratio because it likely accreted this carbon-13 rich material. So again, just like the C to O ratio, the carbon isotope ratio could place another constraint on these formation scenarios. And in fact, for us, the carbon-12 to carbon-13 ratio is the most widely observed of the CNO isotope ratios. So here I show a not quite to scale plot of the substellar objects with carbon-12 to carbon-13 ratios in the literature. So the more massive brown dwarfs are on the left, and then the superjupiters are over here on the right. And I'll just draw your attention to a couple different things. So first of all, all of these carbon-13 detections have been made within the past 3 years, and most of them have actually been published just this year. A lot of the authors are here in the room, which is pretty cool. But these studies use the state-of-the-art near-infrared observatories like VLT CRIRES, NearSpec and CAPIC on Keck. We also have Gemini and iGRINS and even JWST's NearSpec to constrain the abundances of these weak carbon-13 isotopologs. The second thing to note here is that besides the couple of stragglers on the brown dwarf side, we are seeing a potential correlation with the carbon-12 to carbon-13 ratio and the object's mass. So the more massive brown dwarfs are exhibiting solar to supersolar carbon-12 to carbon-13 ratios, while the smaller Jupiter-class exoplanets are showing some carbon-13 enrichment. So this means, again, that the carbon-12 to carbon-13 ratio could be an indicator of the formation process that these giant planets underwent. But again, as of now, this is sort of just based on observation, since there are very few models that actually test beyond elemental abundances and include isotopic ratios and how they differ. Finally, we also see a pretty interesting similarity in the carbon-12 to carbon-13 ratios for the super-Jupiter group. So while 77AB and HD 189733b are both hot Jupiters, transiting close into their host stars, while VHS 1256b and Tycho 8998b are both young, wide orbit, directly imaged planets. But you'll notice that each of these planets, they show a ratio that's consistent with the ISM value of around 68. So what does this mean? This can mean a couple things. First of all, the similar carbon-12 to carbon-13 ratios between the hot Jupiters and the directly imaged planets could mean that carbon-13 enrichment is a signature of formation via core accretion, regardless of where in the disk the formation takes place. The slow formation timescales would allow for the accretion of this carbon-13 enriched gas or ice, but the other possibility is that the carbon-13 enrichment is actually a signature of the planet's formation in the outer reaches of the protoplanetary disk, out beyond the CO snowline, where we expect there to be reservoirs of carbon-13 rich gas and ice. And the second scenario is also supported from a sort of dynamical standpoint because we think that hot Jupiters likely did not form where they are in situ, but instead the victims of something like high eccentricity coplanar migration. But without a host star measurement, it's really difficult to contextualize the extent of a companion's carbon-13 enrichment. And unfortunately for us, most of these host stars don't have complementary isotope log ratio measurements, and it's often difficult to make them in the stars just because of the nature, and we'll talk about that a little bit later. In the literature, there are very few stellar carbon-12 to carbon-13 ratios. So we have a handful of measurements from solar twin stars and a couple of M dwarfs ranging from sub-ISM to supersolar values. But it's difficult to derive isotopic carbon abundances for a couple of reasons. First of all, they're preferentially measured in using CO bands in the near infrared or the near infrared, but it's difficult to obtain high signal to noise and high resolution spectra. The cool dwarfs that we look at also can't be fast rotators. Otherwise, the isotopic log lines just blend away and we can't really do anything with that. In the case of the directly imaged planet host, it's hard to model the spectra in general because of the high activity, the strong magnetic fields, and then the photospheric veiling that sort of distorts their spectra. Out of these stars, there are very few that host exoplanets, and only one, WASP-77A, has a companion with a carbon-12 to carbon-13 ratio in the literature. But I'll just kind of leave it at that. For nitrogen, this will go fairly quickly because there's hardly anything in the literature for nitrogen isotope logs in brown dwarfs, dwarf stars, or even exoplanets. But essentially, we think that the nitrogen 14 to nitrogen 15 ratio will also be important for tracing planet formation because nitrogen exhibits similar fractionation signatures as carbon. So now the disk is sort of split by the ammonia snow line at 5 AU and the N2 snow line at around 20 AU. But you can see that the enrichment sort of changes depending on where you are in the disk. But the sort of breakthrough that's got us talking about nitrogen isotopes in the first place came out just last year in Nature. So there was a minor isotope log of ammonia that was detected by the MIRI spectrograph on JWST in a rogue brown dwarf named YJ1828 that we've heard a couple of people talk about now. But you can see a couple of the lines that they use in their analysis. But in general, this result is really cool for a couple of reasons. First of all, the ammonia features that they use are located around 9 to 11 microns. Typically, our ground-based observatories don't provide much coverage beyond 5 microns, but JWST is great for that. And then because YJ18 is a really cool temperature, this is kind of the only object where we expect to be able to detect these sort of things. But again, JWST is just really, really good at being able to make these measurements. And I'm running out of time, so I'll just kind of skip over oxygen, but we can talk about it offline if you're interested. So I'll leave my final statements here. Just we're characterizing exoplanet atmospheres like never before, but just keep in mind it's really important that when they have stellar companions, it's important that we characterize the companions as well for good context. Keep an eye out for my paper on the WASP-77A system that's in review. We're sort of doing like a formation scenario based on the abundance inventory that we're able to find in the literature. And if you're interested in deriving any volatile elemental or isotopic abundances in anything, come talk to me. Thank you.
So much, David. That was super interesting. We have 3 minutes for questions. So please, if you ask a question, say your name, your institution, and then your question and your comment. So like this, like, hi, my name is Daniela. I am from Amherst College. Hello, everybody. But yes, we have 3 minutes for questions. All right, we'll start.
Hi, I'm Brianna from Grand Lakes. I would love to hear about oxygen.
Okay. So the thing with oxygen is that James Webb is producing some really, really tight constraints on like the oxygen 16 to oxygen 18 ratio. And even in VHS 1256b, there's been a detection of oxygen 17, which is even rarer than oxygen 18. So the fact that we're able to see anything with regards to that at all is pretty crazy. But oxygen is also interesting because in our own solar system, we don't really see the sort of fractionation signature that we're seeing with carbon or nitrogen. So even though we're able to make these measurements in these cool worlds for oxygen isotope ratios, it's unclear if it's actually going to be a good kind of like formation tracer.
Boston University.
Your question?
Was it?
Your question.
At least one hot Jupiter transit.
Mhm.
That might fall into this, all these challenges described, like measuring the ratios. Stars too hot, maybe it's cold enough, maybe it's cold enough. How do I make this a question? Have you thought of that?
I have, and like for that particular reason, I've kind of been avoiding M dwarfs altogether. So I started out kind of doing this analysis in solar twin stars, and now for my next project, I'm going to try to get down to the K dwarfs in the near infrared. But M dwarfs, I'm still a little bit afraid of, but eventually we'll get there. For sure, absolutely. It's important to keep it uniform, especially when we're looking at stellar measurements, which are made completely different than the exoplanet measurements. But then just because of like the differences in temperature, we're kind of limited to, we can only use these molecules for the cool worlds, but we can only use these molecules in the stellar objects. And then each of those molecules is observed at different wavelengths. So like we have optical spectra, we have near infrared, mid infrared, and it's really hard to kind of balance it out. So right now we're just kind of taking everything with a grain of salt because there are so many different ways to go about this.